We have already learned that the remote sensing involves with the data capturing or acquiring from the target object through recording the interaction between the target and the atmosphere and the incident energy. The sensor is a device which helps in gathering information in wavelength of energy. These sensors are usually mounted on platform. In this chapter, we will discuss about various types of platforms and their advantages. Platforms. According to Lillesand and Kafer, a platform is a vehicle from which sensor can be operated. Platform is a stage where sensor or camera is mounted to acquire the data about a target. Platform refers to the structure or a vehicle on which remote sensing instruments are mounted. A platform is a synonym for any orbiting spacecraft, be it a satellite or a manned station from which observations are made. As in most of the cases, the platforms are mounted on the moving vehicle, be it aircraft or satellite. So, as the aircraft moves along its path to the target object also changes. This allows us to have a complete coverage of an area. The platform may be placed on the ground or air or space. As a platform height increases, the spatial resolution and the observational area increases, this covering large geographical area. The satellite orbiting the Earth is a typical platform. However, the platform range from balloons, kites, that is a low altitude remote sensing, to aircraft and satellite, that is aerial and space remote sensing. As altitude determines the ground coverage, it is a key factor for selection of a platform. Apart from altitude, there are other parameters which determine the use of a particular sensor in the platform. These attributes include distance the sensor is from the object of interest, periodicity of image acquisition, timing of the image acquisition, location extent of the coverage. Depending on what type of data to be captured by the sensor, the platform may be varying from ladder to satellite. For some tests, sensors are also placed on the ground platform. In the aircraft, in the satellites are commonly used. Platforms like balloons and rockets are also used. Types of platforms. They are broadly divided into three types of platforms: terrestrial platform, airborne platform, spaceborne platform. Terrestrial platform. Terrestrial platform are also called as ground-based platform, as they remain in contact with ground during the imaging of the Earth's surface. Ground observation platform are used to record detailed information about the object or a feature of the Earth's surface. These platforms are developed for the scientific understanding on the single object and signal sensor interactions. Based on the movement, ground-based platform are either static, that is on the stationary platform such as tripod or a mesh, or dynamic, that is on a moving vehicle used to close range, high accuracy application. These platforms work in short, medium and long range of 50 to 100 meters up to 250 meters and 1000 meters respectively. Purpose of the short range application is the mapping of buildings and small objects. Medium range sensors are having millimeter accuracy and is used for three-dimensional modeling application. Long range sensors are frequently used for topographic application. Ground observation includes both the laboratory and a field study. It is used for both designing the sensors and identification and characterization of the land features. Ground observation platforms include handheld platforms like cherry ladder, tower, portable mesh and vehicles, etc. Portable handheld photographic cameras and spectroradiometer are largely used in laboratory and in field experiments as a reference data and ground truth verification. Laboratory instruments are used mainly for research, sensor calibration and quality control. Most of the laboratory work is used to identify different materials. Field instruments are also largely used for research purposes. They are usually handheld or mounted on a tripod or other similar support. Permanent ground platforms are typically used for monitoring atmospheric phenomena, although they are also used for long-term monitoring of terrestrial features. Towers in cranes are all often used to support research projects where a reasonable stable outcome along term platform is necessary. Towers can be built on site and can be tall enough to protect through the forest canopy so that the range of measurements can be taken from the forest floors through the canopy and from the above the canopy. The data collected from the terrestrial platforms are used for bridge and dam monitoring, common landslide and soil erosion, mapping, architectural restoration, facilities inventory, crime and accident scene analysis, manufacturing, etc. It is incorporated into surveying and meteorological instruments and is often employed in mobile mapping systems. Airborne platforms. With large developments in photographic camera and technology, in aerial remote sensing is now well established with the development of sensors. Airborne platforms are capable of operating in variable altitudes ranging from sea level to stratosphere at an altitude of about 500 kilometers. They facilitate collection of data over virtually any portion of the Earth's surface at any time. Airborne platforms are primarily stable wing aircraft, although helicopters are occasionally used. Aerial photographs are obtained from the airborne platforms are obtained by using mapping cameras that are usually mounted on the nose or under the belly of the aircraft that then flies in a discrete pattern or swaths across the area to be surveyed. Airborne platforms were the sole non-ground based platform for the early remote sensing work. Aircraft remote sensing system may also be referred to as suborbital or airborne or aerial remote sensing systems. At present, aeroplanes are the most common airborne platforms. Other airborne observation platforms includes balloon stones and high altitude sounding rockets. Helicopters are occasionally used. Balloon platforms. Balloons are used for remote sensing observation and nature conservation studies. In 1859, first aerial image was acquired with the camera carried aloft by a balloon. Balloon floats at a constant height of about 30 kilometers. It consists of a rigid circular base plate from supporting the entire sensor system, which is protected by an insulating and shock-proof light erasing. Balloon imagery gives larger synoptic view as the flight altitude being high compared to normal aircraft height used for aerial service. The payload used for Indian balloon experiments is 3-nozzle blade camera with different film filters combination to provide pan, infrared black and white and infrared false color images. In India, at present, Tata Institute of Fundamental Research, Mumbai, has set up a national balloon facility in Hyderabad. The tethered balloons are connected to the Earth station by means of a wire serving high tension strength and high flexibility. Drone. Drone is a miniature remotely piloted aircraft. Its main advantage is that it is a low-cost platform with long endurance, moderate payload capacity and capability to operate without a runway or small runway. Drone includes equipment of photography, infrared detection, radar observation and TV surveillance. Drones use the satellite communication link. Drone was developed in Britain during the World War II in the Short Sky Spy, which was originally conceived as a military reconnaissance. Now it plays an important role in remote sensing. The unique advantage is that it could be located above the area for which the data was required and capable to provide both night and day data. Aircraft. Traditionally, to acquire aerial photographs and images of land surface features, special aircraft with cameras and sensor on vibration-less platform are used. Nearly The whole spectrum of civilian and military aircraft are used for remote sensing application. When altitude and stability requirements for a sensor are not too demanding, simple, low-cost aircraft can be used as platforms. However, as requirements for greater instrument stability or higher altitudes become necessary, commonly more sophisticated aircraft must be used. Aircraft are divided into three categories based on their altitude restrictions. Low altitude aircraft. They fly below 12,500 feet above sea level. They are good for requiring high spatial resolution data limited to a relatively smaller areas come with large scale. This aircraft is inexpensive to fly and can be found throughout the world. Some of these airplanes are specially outfitted for mounting remote sensing instruments in the underside of a plane. However, many times instruments are simply hung out the door using simple mounts. Mid-altitude aircraft. These are an altitude limit under 30,000 feet above sea level. This includes in a member of turboprop aircraft. Often at higher altitudes there is less turbulence, so stability is better. Aircrafts can obtain greater distance than available from low altitude platforms. High altitude platforms. High altitude platforms can fly at altitudes greater than 30,000 feet above sea level. This aircraft is usually powered by jet engines and is used to specialized tasks such as atmospheric studies, research to stimulate satellite platform and other application for a high altitude platform is required. High altitude platforms are good for acquiring large aerial coverage with typically low spatial resolution. The National High Altitude Photography Program 1978, coordinated by the US Geological Survey, started to acquire coverage of United States with a uniform scale and format. Besides aerial photography, multispectral, hyperspectral and microwave imaging is also carried out by the aircraft. Therefore, multispectral, hyperspectral and microwave imaging were also initiated. Aircraft platforms offer an economical method of remote sensing data collection for small to large study areas with cameras, electronic images, across track and along track scanners and radar and microwave scanners. EVIDUS hyperspectral imaging is famous aircraft aerial photographic operation of US Geological Survey. High altitude sounding rockets. High altitude sounding rocket platforms are useful in assessing the reliability of the remote sensing techniques as regards their dependence on the distance from the target is concerned. Balloons have a maximum altitude of approximately 37 kilometers, while satellites cannot orbit below 120 kilometers. High altitude sounding rockets can be used to moderate altitude above terrain. Imageries with moderate synoptic view can be obtained from such rockets for areas of some 5 lakh square kilometers per frame. The high altitude sounding rocket is fired from a mobile launcher. During the flight, its scanning work is done from the stable altitude. The payload and the spent motor are returned to the ground gently by a parachute, enabling the recovery of the data. One of the most important limitations of this system is it to ensure that the descending rocket not going to cause damage. Advantages of airborne platforms. Aircrafts fly at low altitude, thus allowing for sub-meter sensor spatial resolution. Aircraft can easily change the path on time of remote sensing to avoid weather problems such as clouds which may block passive sensor view on the ground. Changes in the flight timings can be made according to the sun's illumination and additional revisits to that location is possible. Sensor maintenance, repair and configuration changes can be easily made to the aircraft platform. There is no boundaries for aircraft path except the political boundaries. However, getting permission is needed in few areas. Space-bound platforms. Man-made satellites are examples for space-bound platforms. It is also referred as orbital remote sensing. In this platform, satellites and sometimes spacecrafts are used as platforms. In space-bound remote sensing sensor mounted on bound a spacecraft orbiting the Earth. Because of this orbit, satellites permit repeated coverage of the Earth's surface on continuous basis. The orbits of the spacecraft are fixed and maintained consistently over the time period. These platforms are either short duration or long duration. Space remote sensing can significantly enhance the information available from traditional data source because it can provide synoptic view of large portions of the Earth. However, resolution is limited due to the satellite fixed altitude and orbital path flown. Space-bound platforms are currently used in scientific and socio-economic activities like weather prediction, crop monitoring, common mineral exploration, wasteland mapping, cyclonic warning, water resource management, and pollution detection. There are two types of well-recognized satellite platforms: manned satellite platform and unmanned satellite platform. Manned satellite platforms. Manned satellite platforms are used as a last step for rigorous testing of the remote sensors on board so that they can be finally incorporated in the unmanned satellites. This multi-level remote sensing concept is already presented. Crew in the manned satellites operates the sensors as per the programmed schedule. Information on a series of NASA's manned satellite programs are present. Unmanned satellite platform. Landsat series, Spot series, IRS series of the remote sensing satellite, NOAA series of meteorological satellites, the entire constellation of GPS satellite and the GEOs, and INSAT series of geostationary, environmental, communicational, television broadcast, weather, and the Earth observation satellite, etc. are examples of unmanned satellite category. Satellites can be classified by their orbiter geometry and timing. Three orbits commonly used for remote sensing satellite are geostationary, equatorial, and sun synchronous. A geostationary satellite has a period rotation equal to the Earth, so the satellite always stays over the same location on the Earth. Communication and weather satellites often use geostationary orbits, with many of them located over the equator. In an equatorial orbit, a satellite circles the Earth at low inclination. Low inclination is the angle between the orbital plane and the equatorial plane. The space shuttle uses an equatorial orbit with an inclination of 57 degrees. Sun synchronous satellites have orbits with high inclination angles passing nearly over the poles. Orbits are timed so that the satellite always passes over the equator at the same local sun time. In this way, the satellites maintain the same relative position with the sun for all its orbits. Many remote sensing satellites are sun synchronous, which ensures repeatable sun illumination conditions during specific seasons. Because a sun synchronous orbit does not pass directly over the poles, it is not always possible to acquire data for the extreme polar region. The frequency at which a satellite sensor can acquire data of the entire Earth depends on sensor and orbital characteristics. For most remote sensing satellites, the total coverage frequency ranges from twice a day to once every 16 days. Another orbital characteristic is altitude. The space shuttle has a low orbital altitude of 300 kilometers, whereas other common remote sensing satellites typically maintaining a higher orbit ranging from 600 to 1000 kilometers. Most remote sensing satellites have been designed to transmit data to the ground receiving station located throughout the world. To receive the data directly from the satellite, the receiving station must have a line of sight to the satellite. If there are no sufficient designated receiving stations around the world, any given satellite may not readily get a direct view of a station, leading to potential problem of data discontinuity. To work around this platform, data can be temporarily stored on board the satellite and later downloaded upon acquiring contact with the receiving station. Another alternative is to relay data through TDRSS, Tracking and Data Relay Satellite System, a network of geosynchronous geostationary communication satellites deployed to relay data from satellite to ground stations. The payload for remote sensing satellites can include photographic systems, electro-optical sensors, microwave or LiDAR systems. For applications benefiting from simultaneous coverage of different sensors, more than one sensing system can be mounted on a single satellite. In addition, the sensor system, they are often devices for recording, pre-processing and transmitting the data. Advantages of space-bound platforms. They cover large area of geographical conditions. There is repetitive and time-bound coverage in space-bound platforms. Quantitative measurements of ground features possible using radiometrically calibrated sensors. Data acquired through space-bound platforms can be used as a semi-automatic computerized processing and analysis. They are relatively lower cost per unit area coverage in long term. They have global accessibility. Summary. In order for a sensor to collect and record energy reflected or emitted from a target or a surface, it must reside on a stable platform removed from the target or surface being observed. Platforms for remote sensors may be situated on the ground or an aircraft or a balloon or some other platforms within the Earth's atmosphere, or on a spacecraft or satellite outside of the Earth's atmosphere. Ground-based sensors are often used to record detailed information about the surface, which is compared with information collected from aircraft or satellite sensors. Aerial platforms are primarily stable wing aircraft, although helicopters are occasionally used. Aircraft are often used to collect very detailed images and facilitate the collection of data over virtually any portion of the Earth's surface at any time. In space, remote sensing is sometimes conducted from the space shuttle or more commonly from satellites. Satellites are objects which revolve around another object. In this case, Earth, for example, the Moon is a natural satellite, whereas a man-made satellites include those platforms launched for remote sensing, communication and telemetry, location and navigation purposes. Because of their orbits, satellites permit repetitive coverage of the Earth's surface on a continuing basis. Cost is often a significant factor in choosing among the various platform operations. Cost is often a significant factor in choosing among the various platform options.